Great to be here this evening and be able to join the RI community, even in a virtual way, if we can't be in the famous Faraday Lecture Theatre this evening. I think it's been about 4 years since I last spoke there, and what I want to do tonight is give you a bit of a sort of an update on the work that I've been doing and my colleagues have been doing around the topic of solar activity and space weather. So even though I've got the title Space Weather, what I want to convey is that space weather is a huge area of research, and the area that I focus on is the sun end of that. What we'll see is actually a chain of processes, and so that also gives me the excuse to show lots of great movies and images of the sun as well, which is a beautiful object as well as a scientifically interesting object. So for those of you who I have met before, it's nice to be with you again, and if I haven't met you before, then as you've heard, I'm Lucie Green. I'm a space scientist working at UCL's Mullard Space Science Laboratory, where my research focuses around what the sun gets up to, but also the impact that solar activity has on us too. So tonight I'm going to be sort of covering rather a lot of the solar system, from the sun all the way out to the Earth. But to start off with, I thought I would just give you a sort of tease. So this is a video here, a video that some of you may have already seen, because last week we were lucky enough to have the first images released from the Solar Orbiter mission, which is a mission that studies the science underlying space weather. And what you can see here are images of the atmosphere of the sun taken by a telescope that was partly built actually by people in my department at UCL. So this is just a tease. I hope that some of you saw the press release last week and got excited about the Solar Orbiter mission. So I'm not going to talk about this movie now. I'm going to come back to it at the end. But what I do want to do is just sort of make the point that when we're looking at the science of the sun, we're also looking at the science underlying space weather. And the Solar Orbiter mission is a spacecraft that's been designed and built and launched to understand changes that are happening throughout the solar system, or processes happening throughout the solar system that are driven by our sun. And so it's interesting for me as a solar scientist to just perhaps sort of start on that thought of the solar system. And, you know, when I say that phrase, you're probably thinking of what your concept of the solar system is. And I would expect that you'd be thinking about the sun in the center of the solar system and the planets and the asteroids and comets in orbit around the sun. So collectively, these objects making up our solar system formed as a family out of a collapsing cloud of gas and dust that eventually led to these objects. But as a solar scientist, we think about the solar system in a sort of, we give it a different definition. I have a different definition of the solar system to one which is merely defined by the planets in orbit around the sun. And so that's where I want to start this talk, by giving you my definition of the solar system. And it's a definition that's based around the physical extent of the sun. So let's start and let's have a look at what the sun is as an object. So in my talks, I like to give a bit of an introduction where we look at the layers of the sun. And that helps me set the terminology that I'll use. And it helps, I think, just set in your minds the physical structure of the sun and what you'll be seeing in the different images and movies that I'll show. So I've got on my slide a sort of segment of the electromagnetic spectrum going from infrared through visible light all the way to shorter, more energetic parts of the spectrum through ultraviolet, X-rays and gamma rays too. And let's have a look at how the sun looks in these different wavelengths of light. So if you have heard me talk before, you'll know that I like to have this as my introduction. So when we look at the sun in visible light, we're looking at light that our eyes obviously can detect. And the sun looks almost like a blank disk, except for these dark spots that you see on the surface of the sun that we call sunspots. And here we're looking at light that's being emitted by the sun, but light that was actually generated in the core via nuclear fusion. So the coming together of nuclei of hydrogen atoms that, in the intense conditions inside the sun, the high temperatures, particles are very energetic, high pressures, you're able to have nuclear fusion happen, which liberates energy creating photons of light that work their way out of the sun, eventually reaching the photosphere after a journey of about 200,000 years, getting to the surface. There, the density of the gas of the sun has dropped enough, we would say the opacity has dropped enough, so that the photons of light can stream out into the solar system and reach us here on the Earth 8 minutes later. So the photosphere is the sphere of light of the sun. And that's the wavelength that we typically use on the ground, because it is a wavelength of light that comes through our atmosphere. But as a space scientist, there's a bit of a giveaway in the title of my job that I want to be able to see the sun from space. And there's a really good reason for that, because there are many wavelengths of light that don't make it through the Earth's atmosphere that the sun shines in. So if I go now to the ultraviolet part of the spectrum, this is how the sun looks. This image is taken at exactly the same time as the previous one. It's just the wavelength of light that's been altered. So I'm now using a telescope that's picking up ultraviolet light. And you can see those dark sunspots are still there, but there's a whole sort of structure of the sun that's now revealed by looking in this wavelength. The sun looks more mottled. There are bright lanes and dark cells. And that's showing us is an indication of the cellular structure of the gases near the surface of the sun, that it's highly, highly structured. And then if I go to a more energetic part of the spectrum, I come into extreme ultraviolet light, the sun looks different again. And now, rather than looking low down towards the surface of the sun, I'm looking in the atmosphere of the sun, a part of the sun we call the corona. And this for me is the layer of the sun that I find extremely beautiful to look at, very visual. What you're seeing are gas structures, plasma structures, which are emitting in high energy radiation because the temperature of the gas is high. Millions of degrees, millions of Kelvin is what the temperature of the gas is in this part of the sun. Now, the other aspect that is important here is not only the temperature of the gas, but it's also the presence of magnetic fields which thread through and emanate the atmosphere of the sun. And the sun has structure because of these magnetic fields. So in the corona, you have giant arches of magnetic fields. And there's a special relationship between the conditions that the gas is in. It's high temperature, it's been ionized, it's in the form of a plasma. And when you have a plasma and a magnetic field mixed together, they influence each other. And there's a piece of science that describes how they are what we would call frozen together. And it means that the charged particles making up the atmosphere of the sun are free to spiral around magnetic field lines. So you think back to Michael Faraday and the concept of magnetic field lines going from a North Pole to a South Pole. Great tool to visualize and communicate about magnetic fields. Electrically charged particles will spiral their way around field lines and move along them, but they can't easily get off of those magnetic structures. And that means in the atmosphere of the sun, the magnetic field sculpts the gas into giant arches, which is what you can see in this image. And then if I go to even shorter wavelengths of light, higher into the X-ray part of the spectrum, now you really can see those giant arches of gas. Highly structured, million-degree gas glowing, glowing brightly and being detected by our telescopes. So that's the kind of basic introduction to the sun. We have the photosphere, well, we have the interior where we have nuclear fusion and energy being generated. The photons reach the photosphere, they're able to stream into space. On top of that is a very hot gas which is liberating its own photons in ultraviolet light or extreme ultraviolet light and X-rays and glowing in those wavelengths. And now you really have what's needed to be able to try and understand why the size of the sun is as it is. So I'm moving on now to the sort of next part of the talk, which is about where does the sun's atmosphere end? Because for me, that defines the size of the solar system. When we're thinking about the atmosphere of the sun, we can't not have an opportunity to look at a solar eclipse. This is an image taken by one of my PhD students when we were in Argentina last year for a total solar eclipse, almost a year ago now, time flies. And Jenny took this photo looking over towards the Andes and the eclipsed sun just as it was approaching sunset. Beautiful, beautiful sight. So you can see the dark disk of the moon that's passed in front of the sun, and then what's revealed around the eclipsed sun is the sun's corona, its atmosphere. Now, in the previous images, I showed you the sun's atmosphere shining in extreme ultraviolet light and X-rays. Here, we're actually looking at photons of light that left the photosphere, interacted with electrons in the atmosphere of the sun, and the photons then got scattered our way. But I like these images because it gives you a feeling for the extent of the visible atmosphere of the sun. So that's one way we can look at the corona, and you see the structure reaching out maybe 1 or 2 solar radii away from the disk of the sun, which has been eclipsed by the moon. But if I come back then to this image I showed you earlier, which is an image directly of the 1,000,000-degree atmosphere, we can start to think about what that really means. And the physics of a hot gas is that it will have a high pressure and it will want to push out into the solar system. And there was, about 60 years ago now, a sort of short series of papers that culminated in a realization that if you have a hot gas like the atmosphere of the sun, which is a very good conductor of heat, so that hot gas stays hot out to large distances, the realization was that there's a really important consequence. And that was a piece of work that was carried out by Eugene Parker, who is still alive. And there's an image of him on this slide being interviewed by Nikki Fox, who is the director of NASA's Heliophysics division. And she's interviewing him because we celebrated 60 years since this discovery. So Eugene Parker realized that in the atmosphere of the sun, given it conducts heat to a large distance, it will have a high temperature to a large distance and a high pressure to a large distance. And it means that the gravitational pull of the sun isn't able to hold on to the gas once you get to a certain height. So he concluded that probably it's not possible for the solar corona, the atmosphere of the sun, or indeed the atmosphere of any star, to be in complete hydrostatic equilibrium. So it's not static out to large distances. And he concluded we expect always to find some continued outward hydrodynamic expansion of gas. So to sort of interpret that, what Eugene Parker realized was that the atmosphere of the sun, once you get to a high enough height, is streaming out into the solar system. It's not contained by the gravity of the sun. And it forms something that we call the solar wind. And that's so important in our concept of the solar system, because it means when I think about the solar system, I think about this solar wind blowing out, carving out a huge bubble that we call the heliosphere. And that bubble encompasses all of the planets that we know going around the sun. And this slide just shows an artist's impression of that. So we've got the sun in the center, that orange dot, we've got the orbits of the planets making rings around it, and you've got a bubble of gas, and then a kind of windsock shaped structure because the solar system is moving from the left of the screen to the right of the screen. So when I think about the solar system, I think about the heliosphere. And the heliosphere is essentially the atmosphere of the sun expanding into space, carried out by the solar wind, and all of the planets live in the atmosphere of the sun. So with that, armed with that information, let's have a look at what it's like inside the atmosphere of the sun. So we're living here on the Earth, inside the atmosphere of the Earth. We know it's a gusty, we can have winds blowing, we can have, thunderstorms and rain, all kinds of weather phenomena. Let's have a think about what it's like in the atmosphere of the sun, which we are also living within. So this is the image that I showed you earlier, but now running as a movie. And you can see these gas structures created by the presence of magnetic fields, but you can see they're dynamic, they're changing over time. This is a movie that's sped up, so the data are actually collected over several hours and they've been compressed down to make a movie that's just, a minute or so long. And what you're looking at here is the occurrence of what we call a solar flare. So this is a flash of light that gives off light across the electromagnetic spectrum from, from radio waves. There'll be some visible emission, but also lots of X-rays and ultraviolet light and extreme ultraviolet light too. So solar flares are bursts of radiation that emanate out into the solar system. And this light travels through space and impacts on our Earth's atmosphere. And that's one of the components of space weather that I'm going to come back to later on. So when these solar flares happen, they give off electromagnetic radiation, some of which is absorbed by the Earth's atmosphere, and it changes the electrical conductivity and the makeup, the ionization level of our upper atmosphere. So that's a solar flare. Then solar flares are so beautiful. This is another movie of a solar flare. So I should say these images are taken by NASA's Solar Dynamics Observatory. All of these images are freely available online, so you can go to the website and download them. This one I love because it shows a solar flare taking place at the limb of the sun. You can see this very bright structure forming because suddenly there's been a huge release of energy which has heated gas in that portion of the sun's atmosphere. Now you can start to see gas raining down along magnetic field lines back to the surface of the sun under gravity. So solar flares are beautiful events to look at. And this is a particularly spectacular one. But what you've seen is a release of energy in the atmosphere of the sun from the magnetic field that heats up the gas and produces this visible spectacle. So they're solar flares. If I go on to the next slide, I want to show you what happens when a whole portion of the sun's atmosphere is ejected into space. So these are the events that I work on in my research at UCL. They're called coronal mass ejections, ejection of mass from the corona. And maybe it's worth keeping in mind the size of the sun. It's equivalent to 110 Earths lined up side by side. So what you're seeing here in this video, again highly sped up, is the eruption of a vast amount of plasma into the solar system, traveling at very high speeds. They can range from, oh gosh, maybe 200 kilometers a second to 2000 kilometers a second. So they really are moving through the solar system. So there are coronal mass ejections, and they head out into the heliosphere and they keep going. So within this atmosphere of the sun, we've got these solar flares, we've got these coronal mass ejections, and we've got the solar wind, which is this constant gusty flow. This movie here is made using data from the SOHO satellite, which is a joint ESA-NASA mission. And I think this for me just sort of sums up what the atmosphere of the sun is really like, because you can see the green circle in the center, that's images of the sun's atmosphere, and then around it we've got images of the very extended sun's atmosphere, and you can see all of these emissions constantly coming out from the sun. You've got bubbles of gas, these coronal mass ejections. That was one that was headed towards us, so it formed a halo around the sun. You've got flashes of light in the atmosphere, and you've also got the creation of very high energy particles, which when they hit the detector, they look like a sort of snowstorm effect. So I hope that conveys that in the atmosphere of the sun, we have lots of activity. It's very dynamic and it's very variable, just as it is inside the Earth's atmosphere. The other thing to mention about this activity is that it varies in frequency over time. So there are times when the sun is not particularly active and times when the activity really picks up. And that follows an 11-year cycle. And the plot I've got here just shows you that rise and fall of the sunspots on the surface, which tracks with the frequency of solar flares and coronal mass ejections. So at the moment, if you look on the right-hand side of the plot, we're in the year 2020, we're at a time of low solar activity. But it's not totally quiet. The sun is still producing flares and producing coronal mass ejections. So that's sort of my introduction to the gusty and variable atmosphere of the sun in which we live. So let's sort of shift our perspective now, because I think our studies of the sun over the last few decades, particularly during the space era, has changed our understanding of the sun. Early on in the space era, we had images like this one taken from Apollo 8 in 1968, showing the Earth looking like a sort of, isolated in the cold vacuum of space. But actually, what we've come to know is that that's not quite the right way to view ourselves, because we're living in the atmosphere of the sun. And so I think about this Sun-Earth chain, that we have the sun in the center of the solar system producing eruptions, producing the solar wind, which propagates out from the sun, travels over 150 million kilometers until it reaches the Earth with our magnetic field, causing impacts on the magnetic field, causing impacts on the properties of the particles within the magnetic field, and also causing an impact on the atmosphere of the Earth itself. So for the next part of my talk, I want to have a look at just a part of that impact and a part of what's driving the impact. So what does space weather mean for us really here on the surface of the Earth, and what's some of the science that's underlying it? So with that in mind, I think we should start by having a look at the Earth's magnetic field, because this really is our shield within the atmosphere of the sun. And it acts as a barrier to what the sun throws our way, but it's not perfect. And changes in our magnetic field ultimately affect us here on the Earth. So to illustrate that, I included this animation from a group at the University of Michigan. So it's a simulation of the Earth's magnetosphere, the Earth's magnetic field. You can see that the Earth is a small blue sphere on the sort of bottom left-hand side. And the arrangement is that the sun is off on the left and the solar wind is flooding over the Earth's magnetic field. And doesn't it look like a windsock blowing in the wind? There's a tail of magnetic field that gets drawn out the back. So again, we're using field lines. The black lines represent the magnetic field of the Earth. A way of visualizing it, as I said already, as Faraday did. And as the solar wind, the gusty solar wind flows over the magnetosphere, it flaps and it moves, it gets compressed on the dayward side and drawn out into a long tail on the nightward side. And this is all happening in the space above our heads, invisible to us, but the magnetic field is there and it's responding to the pressure of the onslaught of the solar wind. So that's the sort of basis of the Sun-Earth interaction. But of course, there's more to it than that. And the next thing I want to do is introduce you to a process that is used a lot in solar physics and magnetospheric physics. And it's a process called magnetic reconnection. And I think this animation here from the University of Oslo really nicely illustrates this process. So again, I've got the sun off on the left-hand side, and the magnetic field of the Earth has been visualized by field lines drawn from the north to the south pole of the Earth. And when the video runs again, you'll see these yellow field lines coming in from the left. That's magnetic field from the sun. And notice the arrows, because magnetic field is a vector that has a strength and a direction. And you'll notice that the field coming from the sun points south, and it encounters field at the Earth, which is pointed north. And that opposite directed nature of those two fields is what we need for magnetic reconnection to happen. And you will have seen the breaking and joining of field lines that reconfigures the field. And in fact, it happened on the left, and then it happened on the tail on the right-hand side. Magnetic field lines breaking and rejoining. And this process of magnetic reconnection is a really important process, because it enables the magnetic field of the sun to be joined to the magnetic field of the Earth. You're cutting and rejoining field lines. And that's significant because it essentially means you can transfer energy that's coming with the magnetic field of the sun's emissions. So for example, this could be a coronal mass ejection, or it could be magnetic field carried in the solar wind. and you can connect the sun's emissions to the Earth's magnetic field, transfer energy, transfer particles of plasma that's also carried by those structures, and dump them in the Earth's environment. And when this animation ran, you will have seen that at the end, there were the northern and southern lights happening. And in fact, if I go back, maybe we can just run the video again. Now I've talked through it. So let me see. Yes, here we go. So in comes the magnetic field from the sun in the solar wind, coronal mass ejection. Here it breaks and rejoins. The field lines become part of the Earth. Energy and particles can be dumped into the Earth system, but the flow carries on over the sun and brings the magnetic field lines into what we call the tail. Oppositely directed field lines meet again, they reconnect, and now you get this slingshot of particles where they follow the field lines, get dumped in the Earth's atmosphere, release their energy there, light up the skies as the northern and southern lights. So there's quite a lot of physics that's being illustrated in what is a sort of potentially very simple animation. But I think it conveys quite nicely what we think is happening in the tens of thousands of kilometers above our heads. So bear in mind that we are living in the atmosphere of the sun. We are partially shielded by the Earth's magnetic field, but not fully, because it's a sort of leaky barrier in that magnetic reconnection can open up the magnetic field and allow energy and particles from the sun to come in. We talked earlier about the solar cycle and how there's an 11-year cycle with peaks and troughs in activity. And I want to just pick out 3 or 4 times now where the Earth's magnetic field didn't fully protect us from what the sun was sending our way, and have a look at what the actual physical consequences were. So we've touched a bit on the science. I'm going to come back to that later, but let's sort of have a little interlude to see, well, what actually does it really mean or matter to us here on the Earth? So I pulled out a few events. And the first event, big space weather event that I want to talk about, happened in 1989. And this is really a wake-up call for space weather, because we hadn't had as significant an impact as this one in modern times. So in 1989, the sun produced a significant eruption, a coronal mass ejection, that travelled through the 150 million kilometres between the sun and us, arrived at the Earth, slammed into the Earth's magnetic field, magnetic reconnection took place, and energy was dumped into the Earth's magnetic field and atmosphere. And one thing that is sort of maybe a sort of physical link here is that when you are changing the Earth's magnetic field, you're inducing electric fields and electric currents. And those electric currents can be flowing up above our heads, or they can be flowing through the Earth itself. And when they flow through the Earth, they can interfere with power distribution lines. And in 1989, exactly that happened, where the power distribution network in Quebec, in Canada, failed within, I think it was something like a minute and a half of these current systems affecting their network. And 6 million people lost their electricity. So there was transformer damage also in the UK as well, but we didn't have the outage that was experienced in Canada. Meanwhile, up above people's heads, we didn't have as many satellites in space then as we do now, but over 1,000 objects in orbit around the Earth were sort of lost in that the tracking of their positions failed, because the energy that was dumped into the Earth's atmosphere caused it to heat and expand, and that changed the drag on the spacecraft and changed their orbits. So things are, practically happening on the ground underneath our feet and in the atmosphere above our heads. So that was an event that happened in 1989, and it was really a time that made people think, gosh, the sun can really have an impact on our technology, and we need to start being better at our ability to understand what that impact is and forecast so that we can mitigate the risks. So if I come forward now into 2003, there was an event that took place which was my first experience of space weather. And this was a time where the sun produced several coronal mass ejections, in quick succession over a small number of days that slammed into the Earth's magnetic field. It produced a large series of solar flares whose radiation was absorbed by the Earth's atmosphere that changed the ionization level, heated it, and caused it to expand. And also, the sun's activity sent very high energy charged particles, like a sort of lighthouse beam, in our direction as well. And those high energy particles can make their way through the Earth's magnetic field and into the atmosphere and can cause radiation problems. So I remember this event really well. I was quite an early career scientist at the time, but it was my first experience of seeing that impact. So what happened? Well, during this time, 47 satellites had temporary outages. 10 satellites lost their service for over a day. There were GNSS position errors. So GNSS is the Global Navigation Satellite System. It's sort of the generic term for GPS, which we use to get our positional information from using maps. So, yeah, I don't know, your navigation tools on in your cars or on your phones, but also the GPS spacecraft provide timing information. So, for example, on bank transactions. So GNSS is a sort of very fundamental technology that our modern society relies on, and changes in the atmosphere of the Earth because of solar activity cause delays and problems with the satellite signal coming through from the GNSS satellite to us here on the ground. So you get errors in your position and errors in your timing information. There was also a severe impact on aircraft, and this is what I remember very, very well, that some airlines grounded their aircraft because changes in the atmosphere of the Earth caused problems with high frequency radio communications. The signals didn't bounce around on the using the atmosphere as they should do, and also there was a worry about the dose of high energy particles coming from the sun. And then also in Sweden, there was another blackout that affected 50,000 people. So still a very significant number of people. And you bring all these effects together, they are global and they are varied. And that sort of shows really the challenge of space weather forecasting and the need to have lots of people looking around the world doing studies about what's happening locally for them. So that was in 2003. And then another example I want to raise happened in 2017, and it's a different kind of event again. So there was a very large solar flare that happened. And when a solar flare happens, yes, we have high energy radiation that is absorbed by our atmosphere, changing the ionization level. But solar flares also give off a lot of radio emission. And during this event in 2017, there were radio blackouts, partly caused by the fact that the sun's very significant radio emission swamped the signals that were being used by technology here on the Earth. And that coincided with the emergency response in the Caribbean to a hurricane that was coming through. So again, you know, critical times where space weather can impact our technology, and this time especially critical because there was an emergency response going on and they absolutely needed to be able to coordinate. And then finally, my one sort of last example is a space weather event that happened in 1859. And again, for people who are interested in space weather and have read a bit about it, you might have heard of this event because it gets called the Carrington Event, named after Richard Carrington, who was a sort of amateur astronomer who was drawing sunspots on the sun and noticed a flash of light in the sunspot group he was drawing. And you can see that sunspot group superimposed on a grid of the sun in this slide. And this flash of light, we now know, was the first example or the first observation of a solar flare. What we also know is that at the same time, what was totally unknown to Victorian astronomers was that a coronal mass ejection, a huge bubble of magnetized plasma, was also heading away from the sun towards the Earth, and it reached us 18 hours later. Now, back in 1859, there was a huge impact from this arrival of the sun's emissions, but the impact was more of a visual spectacle in the form of the northern and southern lights. There was also an impact on the technology at the time. Cutting edge technology was the electric telegraph, and that was definitely affected and interrupted. But we know it was a very significant space weather event. And the Royal Academy of Engineering carried out a study a few years ago now to say, well, that was a very large event, probably larger than any we've had in modern times. Let's imagine what the scenario would be if it did happen today. What would the impact be? And they predicted that 10% of satellites in orbit around the Earth would experience temporary outages lasting hours to days. And that's significant because we rely on satellite technology. You know, we get our weather forecasts, we get our TV, we get our positioning, timing information, disaster relief, so many functions that satellites hold now. As well as having a massive financial impact, it would have a very substantial societal impact too. In the UK, the National Grid's analysis is that maybe 1 or 2 nodes would experience disconnection. So there would be loss of power for some people in the country, but not somewhere central like London. But there still could be an impact. And then GNSS, which is this fundamental technology we all use, even though we don't necessarily know it, could be inoperable from between 1 to 3 days because of disturbances in the atmosphere. And this report and its findings are very significant because it means that we would have a major impact if one of these very large events happened today. And we think that the Carrington Event of 1859 is sort of like the reasonable worst case scenario of what we might be able to experience here on the Earth. And there's lots of work going into how frequent this kind of event might be, and to make sure we understand what the impacts would be. Okay, so let's move on now to looking a bit more at the science underlying space weather. And here I have to confess, I'm very much focused on the kind of science that I'm involved with and the areas that we're looking at UCL. And I want to come back to the coronal mass ejections, because it is these eruptions from the sun, when they reach the Earth's magnetic field, that can have some of the biggest impacts. So we have a main goal to understand how coronal mass ejections form. Can we forecast them? And what's their magnetic field structure like? Because when they reach the Earth, the orientation of the magnetic field in this erupting structure will affect how readily it engages and interacts with the Earth's magnetic field. So if you remember earlier on when I was talking about the importance of having a southward magnetic field, so it reconnects with the northward field of the Earth. Let's have a look at that. This is one of my favourite pictures of an eruption from the sun. So what we've got here is the size of the sun shown in the white disk. It's occulted in a sort of artificial solar eclipse so that we can see the atmosphere of the sun and we can see the escaping eruption on the bottom right hand side. And what I love about this is that it has a structure, and a very specific structure. It looks helical. And this is something that's of great interest to me in my work. And one of the things we've been looking for is helical structures as they erupt from the sun. So a helical structure like this that we're seeing here is something that we call a flux rope, a twisted bundle of magnetic field lines along which electrically charged particles, the gas of the atmosphere, is trapped. So they are tracing out the magnetic field structures. So we're looking at photons coming from that structure, but the photons are coming from where the gas of the structure is. So we have evidence that the sun ejects flux ropes into the solar system. But what we want to know is actually what's the magnetic field of that helix actually like. And I've got, as a way of illustrating that, some cartoons. So I want you to visualize in your head this erupting structure that you can see here with a twisted bundle of magnetic field lines. And imagine it coming towards the Earth. So how would I go about working out what the magnetic field configuration is like? It's like a corkscrew, but how is the field pointed? You know, which way does it run up the axis, and is it a left-handed twist or a right-handed twist? So with my colleagues who look with me at these twisted structures, we spend a lot of time in our lab doing this with our hands, thinking about a left-handed twist or a right-handed twist. So I wanted to spend a few moments now trying to convey to you what this research is, how we're going about it, and why it's relevant for space weather. So I'm going to take a sort of highly simplified magnetic flux rope structure and have a think about how it could be oriented in space. So I've got snapshots from a paper that's fairly old now, actually. It shows you how long we've been thinking about these flux ropes for. But let's imagine this is a sort of chunk of a flux rope headed towards the Earth as a coronal mass ejection, carrying plasma from the sun with it. So this is highly abstract, I know. Magnetic fields are, but have in mind that this is a physical structure coming towards the Earth. It's a twisted magnetic flux rope about to collide with the Earth's magnetic field. Okay, so let's assume we have a twisted magnetic field structure that has a left-handed twist. Now, I can either, if I do my left-handed twist, point my index finger to the right or to the left, which signifies which way the magnetic field is running through the axis of my flux rope. So I hope you're... So these two figures here on the left-hand side show a flux rope with a left-handed twist. And in fact, let me use my thumb. My thumb points to the right in the top one, and it points to the left in the bottom one. So if you look carefully, you'll see there are arrows on these field lines. And that means if this structure is coming towards the Earth, I'm interested in what the magnetic field orientation at the front of that structure is, because that's what's going to collide with the Earth's magnetic field and decide whether reconnection happens or not. And I am more interested in a magnetic field on this flux rope that points south. So let's have a look. I put arrows in here to show the direction of the magnetic field at the front of the structure. So the top one, the field lines point to the north, and the bottom one, the field lines point to the south. So in my earlier slide here, I know I have this twisted structure coming towards the Earth, but I don't yet know if it's going to cause a big space weather event because I don't know what the magnetic field configuration is, and that's a key driver in the impact and response of the Earth's magnetic field, and whether electric currents will be set up that will affect, produce the northern lights or accelerate particles to impact our spacecraft and so on. So I want to know about the magnetism of this structure. Okay, so that's for a left-handed structure. I can do the same for a right-handed structure, and I can draw my cartoon flux rope, and I can say, okay, if my thumb points to the right, I've got a helix like this in the top, and if my thumb points to the left, I've got a helix like that at the bottom. And I can again think about what the orientation of the magnetic field is at the front of this structure. So this is the challenge that we have, that we're trying to work out. When a coronal mass ejection leaves the sun, what is its magnetic configuration like? And that's a really hard challenge, but it's one that my students have taken up working with me on, thank goodness. So I want to show you some results from another one of my students who's graduated now, but Alex James. And he was looking at the sun a few years ago. So this is a picture of the corona of the sun, the atmosphere, and this is a zoom in of the source region of a coronal mass ejection. And you can see it brightens over time. There is some flaring activity. And then as time goes on, let me see, I think now there's a very faint eruption that leaves the sun and a big flare that's formed underneath. And we wanted to know, well, that structure that left the sun, what was its magnetic field like? Because that's the key piece of information for understanding space weather impact. And Alex's approach was to create a model of the magnetic field in this region of the sun. Now, I don't have too much time in the talk, so I've cut out a lot of his results, but what I want to show you is what he found in his magnetic model. So we use observations of the sun, we use observations of these gas structures that are sculpted by magnetic fields, and we use observations of the magnetic field measured in the photosphere where the sunspots are. And those two data sets allow us to extrapolate the three-dimensional volume of the magnetic field in this CME source region and verify it against observations. And the next slide shows you what he found. So this is a zoom in now. This is a model of the magnetic field of the structure that then went on to erupt. And again, we're using lines to illustrate the magnetic field, where it's bunched together, how it's structured in space, a strength and direction. And can you see the right-handed twist of this structure? So at home, as this video comes round, see if you can kind of trace out the field lines, especially as it turns here. So come up from the foot point and you can do a right-handed turn in these field lines. So Alex created this model, validated it against observations, and found a right-handed twisted flux rope that left the sun, which is so important because it means then we know what's headed in our direction. As a slight aside, again, I don't have too much time to talk about the details, but you can also get information from these magnetic models that helps us understand when an eruption will take place. And this is a snapshot from his paper. So this hasn't been made really, you know, for public consumption. This is from his scientific paper, but I hope it illustrates the point. So you can see that right-handed twisted flux rope, those field lines. And what he's done is also consider the surrounding magnetic field of this flux rope, because the whole atmosphere of the sun is filled with magnetism. It's filled with magnetic fields. And whilst my flux rope erupted up, there's overlying magnetic fields that can help hold this structure down. And what these two slices here show is the strength of that restraint of the overlying field. And we know that the overlying field is unable to hold down the erupting structure if we reach a value of 2 in this particular parameter that's been calculated. So this is a figure here really to show that Alex found the erupting structure, he found that twisted flux rope, and he also showed that it was one that was able to erupt into the solar system and not be held down by the overlying magnetic field. So we've done a lot of work around identifying flux ropes on the sun. And in the previous talk I gave at the Royal Institution, I talked a bit about this then as well, and I talked about it more from an observational perspective. So this is a kind of update from a modelling perspective to show that the ideas that we have, I think, are broadly along the right lines. So we want to know what's happening in these coronal mass ejection source regions because we want to understand the physics. But we're also asking questions, can we use this to predict space weather at the Earth? And that's harder. So my next slide shows you the results of some work we did in collaboration with another PhD student at the University of Helsinki, who looked at what actually arrived at the Earth. And she looked at what we call in situ data. So imagine in your mind's eye this flux rope erupting from the sun, traveling 150 million kilometers through space, arriving at the Earth. And as it does so, the whole structure passes over some of our spacecraft. And those spacecraft have the ability to measure and sense the magnetic field of that eruption. And you can put that together and reconstruct the flux rope that's passing through the solar system. So we just did a simple study where we said, right, well, we see these flux ropes at the sun, we see how they're twisted, and we see how they're angled on the sun. Let's see if that's preserved at the Earth. And this is a figure from her paper. So let me explain this. So we categorized these flux ropes at the Earth into right-handed events and left-handed events. And this figure shows what their orientation was at the sun, that's shown in the yellow spots, and what the orientation of the flux rate was at the Earth in the black spots. And the lines connecting the yellow to the black show that flux rates, as we saw them at the sun, had actually rotated by the time they got to the Earth, sometimes by quite significant amounts, which is not really what we were hoping to find, because it means if our whole structure rotates, we can't accurately forecast what the space weather impact will be, because we don't know with enough time, how big that rotation will be. So this is really here to say, yes, we've found some really interesting things. We've been able to reproduce twisted flux rates. We see them at the sun. But the next challenge is, as these flux rates propagate from the sun to the Earth through the solar wind, we need to be able to understand how they rotate and how they deform before they get to the Earth, so that we can accurately predict how the interaction will go between the magnetic field of the flux rate of the coronal mass ejection and the magnetic field of the magnetosphere. That's a very sort of quick whistle-stop tour of the work around coronal mass ejections, the impact of space weather. Now I want to bring us back to where we started with Solar Orbiter, which is our latest mission to understand the science of space weather. And I think it's timely to talk about it because the mission is in its early phases and we're just sort of getting the first data in now. So for those of you who haven't heard about Solar Orbiter before, it's a European Space Agency mission that was launched back in February this year. It's a mission that carries 10 telescopes on board, has a huge European involvement, and it has two families of instruments. One that is looking at the sun using images, telescopes, the kind that I would use, taking pictures of the sun's surface, the sun's atmosphere. And the second family of instruments are the ones that measure the emissions from the sun as they wash over the spacecraft. And that's a very powerful combination of instruments. Solar Orbiter was launched back in February this year from the Cape Canaveral launch site in Florida. And because the group I work in at UCL has spent, oh gosh, I don't know, I think I first worked on Solar Orbiter 15 years ago, thinking about science we could do with Solar Orbiter. And then engineers got involved to do the design and build. So lots of people in my department have put a significant amount of time over the last years developing this mission. So we went over to watch it launch, which was fantastic. And we watched from here, which is the Banana Creek viewing platform. I think it's about 5 miles from the launch site itself. So we had this amazing view of the rocket going off. It was a beautiful, clear night. Launch went perfectly. But it was silent for 25 seconds because the sound hadn't yet travelled to us. So the light travels so much faster. So the sound took 25 seconds. So you can go away and check whether I got my distance right. Is it 5 miles? You can work that out from the speed of sound. So that was an amazing, amazing experience to see the spacecraft go. We're hugely lucky. And the spacecraft is functioning really well. All the instruments have been tested. We call this the commissioning phase. And this is an ESA schematic just to show the launch. So here we've got the sun at the center of the solar system and the planets Mercury, Venus and Earth. And then the white line, the white dot going around is the Solar Orbiter spacecraft after having been launched from the Earth, getting some gravitational assists from Venus and the Earth. And you can see the interesting orbit that Solar Orbiter is moving into. So it's working its way into a highly elliptical orbit that takes it very close to the sun and then further away from the sun. And Solar Orbiter is a mission which is designed to sort of be, I don't know, filling the missing link. It's designed to get data closer to the sun, or get images closer up to the sun, closer than we've ever been able to take images from before. And not only that, the orbit is being shifted so that rather than just being in the plane of the planets, it gets tilted and it comes out of the plane of the planets, allowing us to see the North Pole and the South Pole of the Sun, which we've never seen before. So for the first time with Solar Orbiter, we'll actually be able to see the whole Sun. And then the images that we had released last week were then the first images taken from close up to the Sun. So Solar Orbiter is still working its way in. These images were taken at a distance of about half of the Sun-Earth distance. And even at this distance, we still had surprises. And in these images, you can see little flashes of light, which are like mini solar flares happening in the atmosphere of the Sun. And a lot of the data we are collecting for the first time. So Solar Orbiter will help us understand the science of space weather. It will help us understand the processes involved in solar flares. It will help us understand the processes behind coronal mass ejections. It will measure the magnetic fields of coronal mass ejections as they come over the spacecraft much closer to the Sun than we've ever been able to do. Well, combined with images, they will give us a close-up understanding of what the magnetic field configuration is of these eruptions. And there's a whole suite of telescopes on board, as I mentioned, that allow us to image the Sun from inside and out, basically. So this is just a schematic from the ESA website. If you want to go and have a look at that, you can find out more about how the orbit's going to evolve over time and the sort of key milestones within the mission. So I'm aware that I've been talking for quite a long time. So let's move on. I've just got two sort of final points now to make. So maybe another 5 minutes. And I want to also mention the work that's being done with the Parker Solar Probe. So cast your mind back to earlier in the talk when I talked about Eugene Parker, who realized the Sun emits a solar wind because its atmosphere is expanding into space. There's a lot we don't know about the solar wind, and it's a key component of space weather. So we know the kind of overview of why the wind forms, but we don't know exactly why it moves at the fast speeds it does. Why does the solar wind have fast streams and relatively slow streams? Parker Solar Probe is going to be looking at that question. Parker Solar Probe was launched a couple of years ago now. It doesn't carry the same suite of imaging telescopes on board that Solar Orbiter does. So here I've just got the animation of the launch and the spacecraft leaving the rocket fairing. But even though Solar Orbiter gets very close to the Sun, so it will get to within, I think it's just over a quarter of the Sun-Earth distance. It will get to about 42 million kilometers. Parker Solar Probe gets about 7 times as close to the Sun. And it gets really into the corona. And it gets into the region of the corona that's important for the formation of the solar wind. So even though Parker Solar Probe doesn't carry lovely telescopes to take images of the Sun, it's going to measure the region in the corona where the processes are happening to help accelerate the solar wind out into the heliosphere. So what's happening to the magnetic fields there? The particles, how are things getting heated and sped up? And there's been some first results already with Parker Solar Probe, and they've been amazing. You'll be able to find the press releases online. The environment closer to the Sun is, I mean, this is the closest we've ever been to the Sun with any spacecraft. The environment is much more complex and dynamic than we ever imagined. Lots of high energy particles events washing over the spacecraft. Interesting, unusual shapes in the magnetic fields as they come out from the Sun. So I'd encourage you to go and have a look at that online. I just want to give you an awareness of Parker Solar Probe. And then one other kind of more more of a throwaway thing about Parker Solar Probe is that it kind of tickled me as well when it launched, because my husband's name is Parker. So strictly speaking, I'm Professor Parker, and on the spacecraft you could have a sort of ticket that had your name on it. So I had my name put on the spacecraft. So Made me laugh because the only time I take my husband's name is when it's going to be sent into space, but this was an opportunity that I couldn't miss. So some of you who are listening may indeed have also done this, put your name on the Parker Solar Probe and sent it off on its mission to get daringly close to the sun. Okay, so finally, the last mission I want to give a plug to is another European Space Agency mission, and it's called Lagrange. And this is a mission which learns from and follows on from the science missions that we use and we've been developing, like Solar Orbiter. But it has a different job to do. So the Lagrange mission will be Europe's dedicated space weather sentinel, and it is being designed to give us observations and data that will allow us to improve our space weather forecasting. And it's a mission that we've been working on at UCL for, oh gosh, several years now, 5-6 years, something like that. And the early preparations are underway, hopefully with it being launched in the mid to late 2020s. So we don't have any data yet, the mission hasn't launched. So I just want to show you where Lagrange will go in the solar system, because we've learned so much about space weather. We know what we need to fill gaps in our knowledge to help us with forecasting. So I mentioned that Solar Orbiter is in a mission to get in an orbit to get close to the sun. We've got a different kind of orbit in mind for Lagrange, and it's an orbit that will allow us to look at the sun and the earth from the side. So I've got a little schematic here in the bottom right hand side of the slide. So we've got the sun in the center of the solar system looking from the top down, earth to the right, and Lagrange is going to be placed in that red circle, which is about 60 degrees off the sun-earth line. And there's a particular orbit that you can put the spacecraft in that will mean it will stay at that point. And that point in the solar system is called the fifth Lagrange point, which is why we have the Lagrange name for the spacecraft. But the point is that as the Earth moves in its orbit around the sun, the Lagrange will always stay 60 degrees off the sun-Earth line. So the spacecraft will be looking at the sun on the left and the Earth on the right, and it will see everything that travels through space towards the Earth. Not only that, but because of the way the sun spins, the Lagrange spacecraft will be looking at sunspots and solar flares and coronal mass ejection source regions before they get into the firing line of the Earth. So this is a really important mission, and it's been very cleverly designed, and that should be launching in a few years' time. So I appreciate that was a bit of a kind of whistle-stop tour through solar activity, space weather, with a lot of talk about abstract magnetic fields and flux ropes, but hopefully the concepts sort of settle and the importance of magnetic fields has come across. My last slide is then just a plug for other work that happens at UCL that I'm involved with, which tries to help take these scientific concepts and make them meaningful and useful for different communities who need them. So I talked about the fact that space weather impacts can involve loss of power, can involve interruptions to GPS, can involve problems with airlines. So there are many sectors out there that we want to engage with and talk to about space weather. And one is by giving talks, running workshops and so on. And another one is by publishing reports. So we've worked a lot with the Risk Reduction Unit at UCL, the Institute for Disaster and Risk Reduction, to produce different reports that look at how does space weather impact the finance sector? What does it mean to build resilience in an organisation to help against space weather impact? What does it mean if you lose your GNSS or your GPS signal? What's the impact of that? What does it mean if the lights go out because we lose power? So if you're interested in reading more, or perhaps you work in a sector that this would be useful, please go to the UCL website. If you go to my website, there's a space weather link, and they're all on that space weather link.